In this question on propulsion systems, we are required to do a momentum analysis of propeller thrust. Okay, if we look at the diagram, you will notice there are two control volumes we have drawn. Outer control volume and an inner control volume. And we have drawn the two streamlines that bound the propeller. The first streamline and the second streamline, and both of them bound the propeller, which is located on an inner control volume. The momentum force on that inner control volume we will give S, label it S. There is now an external control volume drawn round the extremities of the streamline, the two streamlines, and essentially the thrust created will be the same as the thrust S, because there's only one component that is producing a momentum change in this situation, that is the propeller. Now it's important to realize that if we look at the pressure versus the distance along the streamline, we'll notice something very interesting. You notice that very far away from the turbine, the propeller rather, the stream lines indicate that the pressure is atmospheric. As we progress towards the propeller, what happens is the pressure drops to below atmospheric pressure. And what the propeller essentially does is, through its configuration, increases the pressure after the propeller, and as we move away from the propeller, the pressure again drops until very far away from the turbine you have atmospheric pressure restored. Now, as you can see, pressure increases across the propeller. Now, there is a common fallacy to think that across the propeller the velocity increases. No. Look at the velocity before and the velocity after. Because from continuity, the volume before and after the propeller is essentially the same, the velocity before must be equal to the velocity after. Why? This is due to the principle of continuity. You remember A1 V1 equals A2 V2. What is A1? The area before the propeller. Remember, you have to imagine this is a three-dimensional situation and you're looking at a plane section. So A1 and the velocity is V. After the propeller, it is A2, which is equal to A1. So the velocity after the propeller must be the same. The difference is the propeller creates an increase in pressure. So don't forget this. Now, what we have to do once you understand this very important basic concept is, one, we have to show that the thrust on the propeller S is given by the difference in the square of the velocities v2 and the velocity v1. You notice the vector for the velocity v1 I have drawn as a longer line compared to the velocity v1. Okay, so essentially the velocity increase is because you notice the stream tube converges. You are also supposed to show that the velocity at the propeller is the average of V1 and V2. And finally, we are asked to determine the expression for the power required. Now let's get cracking. Now let's look at the two assumptions, or not really assumption, they are notes which we have to be aware of before we perform our derivation. The first is the inflow velocity. The inflow velocity V1 into the control volume is equal to the forward speed of the aircraft or the propeller. Next, V1 and V2 are taken at sufficient distances from the propeller so that P1 and P2 are atmospheric pressure. Let's look at what our equation means. Remember, what are the pressures we are talking about? At the start, the pressure is atmospheric pressure. The pressure drops from atmosphere right until the lowest pressure, P low. Across the propeller, the pressure rises from P low to P high. When it hits P high, as we progress along the streamline, the pressure drops until very far away. The pressure is atmospheric, same as the atmospheric pressure very far before the propeller. What we have done is we have written Bernoulli's equation from point very far away to the point just before the propeller, where the conditions here we consider 1, the conditions here we consider 2. But we cannot use 1 and 2. We have to use the condition here as the condition where the velocity is in fact v. Okay, so Now, let's look at what I've written. Bernoulli's equation, taken from 1 to just before the propeller. You can now see the second equation is just writing the Bernoulli's equation from just after the propeller to the point 2. Okay, the terms are similar as for the first Bernoulli equation. You notice that we can now simplify. We will now subtract equation 1 from equation 2. Okay, as you can see, what we can do is the PA will cancel out, the half rho V squared will cancel out, leaving PH minus PL is equal to half rho V2 squared minus V1 squared. Next, let us consider conditions at the inner control volume, that is around the propeller. S, the overall momentum force, times the pressure force difference is equal to the mass flow rate, momentum leaving minus the momentum entering, which is the same velocity. So this cancels out significantly to 0. And basically, if you look at m dot, it is the density times the area times the velocity. So this equation now simplifies to the momentum force acting on the air is equal to the area multiplied by the difference in pressure. Remember, this S is the momentum force acting on the air. So this will create a reaction equal and opposite on the propeller to move it according to the diagram from right to left. Finally, we combine this momentum equation with the initial Bernoulli equation to get our first answer. Now, writing the Bernoulli equation for the outer control volume gives T is equal to the mass flow rate times V2 minus V1. So, since T is equal to S, we now get our second answer by equating these two equations. I leave it as an exercise for you to evaluate V, which is equal to V1 plus V2 over 2, which is the average of V1 and V2. Our velocity V at the propeller is an average of the initial and the final velocities divided by 2. And finally, the power is equal to the force on the propeller, which drives it forward, in this case from right to left, and the velocity V, which is the average of V1 and V2. Remember, V1 is the aircraft velocity and V2 is the velocity after the propeller. This ends this example.